Welcome. Let's look at 7.3, the integration by parts. We will just spend one day on integration by parts. It is a repeat. I believe we did this last year. That pay no attention to because we didn't do that assignment. So integration by parts, this works for integrating things that came out of like a product rule. And we'll also talk about tabular integration, a nice quick method for integration. So I'm going to pass by those. Let's just go ahead and get our process going here. Integration by parts. We set up a U substitution, so we identify a U. We'll let U equal fx or some function. And then dv will also equal some function. It will be considered a derivative function so that we can integrate it to come back to v. So if I integrate dv, I will get v. If I take the derivative of u, I'll have du. So you know when you take the product rule, you have f times g, and it becomes derivative of the first times the second plus derivative of the second. Oops, we did it different. Derivative, how do I want to say this? The first times the derivative of the second plus the second times the derivative of the first. That's one way of doing it. I typically always put this in front, but when I do product rule. But it doesn't matter because it's just addition. Now, when I see a format where I have f times g prime, then I can integrate that into two spaces. And it turns out then that we end up with a u dv equals, the integral becomes u times v minus the integral of v. Hopefully we create something that's easily integrable. Okay, so integration, selecting the u and the dv is the critical piece for integration by parts. The dv, choose something that's complicated, but yet something that can be integrated. So for the v, choose the most complicated part that can still be integrated. For u, it'll be something that becomes simpler when we find the derivative of it, when it's differentiated. One way to kind of help you out, and you might want to put this, I don't see a spot for you to do this, liate. So use logs or ln's for my selecting u. So you better write selecting u priority. If there's a log or natural log present, choose that for your u, because I can take the derivative of those. Finding the integral of them is much more difficult. I stands for inverse trig functions. A stands for algebraic terms. T stands for regular trig functions, like sine, cosine, tan. And E stands for exponential, oops, didn't need an extra E, exponential terms. Okay, so that's kind of our priority for selecting U. That helps a lot when you're doing these. Rules for choosing U, let's see. For this one, if I have x e to the 3x, I have an algebraic term as well as an exponential term. So I'm going to let the algebraic, because I'm thinking liate, algebraic before exponential. So we're going to let u equal x, and then that will, so this will be my u, and then this is going to be my dv. dv is e to the 3x dx. I think downwards is derivative, so du equals dx in that case. Going upward, finding v, means I need to integrate this, and it is a u sub, so I could let u equal 3x, then du equals 3 dx. Oh, I have a 1/3 du equals dx. Otherwise, e is pretty easy, e to the u du. is pretty easy to integrate, isn't it? Have you noticed, and by now you have a little more experience with integrating, that if I have my u with a coefficient, that the correcting factor is a 1/3. So this will become a 1/3 e to the u is what my v will turn out to be. Oops, instead of u, let's put the 3x in there. Okay, now let's lay it out. So the pattern, I want to see the pattern here. Can I pull this? Yes, perfect. I want to bring that down into our workspace. I'm going to set this up so that I have the integral, that this is my u and this is my dv. My u, my dv. Turns out that that'll be u times v, and my u was x. My dv, I'm sorry, my v was 1/3 e to the 3x. I need to subtract the integral of v du. So I'm going to subtract the integral of v, 1/3 e to the 3x dx. And that's the layout for integration by parts. So the first part is easy to handle, the u times v. We are making progress, aren't we? We got 1/3 x e to the 3x as part of our integral, or antiderivative. Now I need to integrate e to the 3x again. I've done it once already, so I know what this turns out to be. I have the outer 1/3, and I bring in a new 1/3 e to the 3x plus c. And I no longer have any integrals, so this will turn out to be a 1/3 x e to the 3x minus 1/9 e to the 3x plus c. Very recipe driven, the integration by parts. If you can select your u and your dv, it kind of drives itself from that point forward. And I guess you need to memorize the integral pattern for that. The next one we got is x cosecant squared dx. Choose the most complicated part that you can still integrate as your dv. Can I integrate a cosecant x? I think I can, right? That's somebody's derivative. So that's going to be my dv, all of that. And then this little part, the algebraic term, is going to be my u. If I think about Lie8, algebraic for trigonometric. So u will be my x. Let u equal x, and cosecant squared x dx will be our dv. The derivative on this side will be dx, and integrating, remember you're integrating because you're going up. I always build my box the same. That way it's just kind of memorized patterns. Integrate cosecant, that would have to be a negative, cotangent of x. And if I always take, now if I take the derivative, does it swing me back? Yep, because it will become positive, won't it? All right, I feel comfortable with my setup for my parts, and let's go forward then. It's been a while since I've done these. U times v minus the integral of v du. There's our pattern. So u times v. It always turns out, if I build my box this way, that I'm multiplying the top two lines. And that would make this a negative x cotangent of x minus the integral. And then in this box, I come back across the diagonal, and that is the v du pattern. So I'm going to have a negative cotangent x dx. And looking good. That'll be positive, won't it? Now, the first part is just fine. And are you a little bit worried? I'm a little bit worried. What is the integral of cotangent x? It's actually one that is on the memorization list for integrals, and it has an integral that looks like natural log absolute value of sine x plus c. So look on your gold sheet. It's probably near the bottom, and you'll find the integral of cotan. So anything that doesn't have a nice derivative, and we're working backwards, is going to probably be one of these crazy ones. So the integral of tan, the integral of cotan, the integral of secant, and the integral of cosecant all are some sort of natural log pattern. All right, then we come to the integral of natural log, and you're like, I don't know the integral of natural log. Not one of the ones we memorized, but we're going to prove what it turns out to be. So with Liate, we hit it right away, don't we? We hit natural log. So it says, let your u equal the natural log, because I don't know the integral. So that would be difficult, wouldn't it? Since that's what we're trying to integrate in the first place. Du equals 1 over x dx. And then dv would have to be the dx. And then integrating that would lead me to x. Remember, this one we're going uphill, this one we're going downhill. We're taking derivative on the left and integrating on the right. So how did I do that? I said this is my u and this is my dv. Seems interesting, huh? So we know that the pattern goes u times v minus the integral of v du. U times v, multiply across the top. That'll give me an x natural log x minus the integral. Now I'm coming across the other diagonal of x times 1 over x dx. And let me erase my pattern. Simplify. Oh, hey, this is easy. X natural log x minus x plus c. There is the pattern for natural log x. If you want to look it up on Google, just ask for the integral of natural log x, and I think you're going to come out with the pattern there. Maybe something you want to memorize? I don't know. It's not too hard to integrate it either by parts. All right, we got this is a long section. Integral of x squared e to the 4x. So algebraic before exponential. This has to be my u. This has to be my dv. It's u is x squared, then du is 2x. dv is e to the 4x dx. If I integrated e to the 4x dx, I would set up a little u sub, wouldn't I? Can you already predict what the adjustment factor has to be? Let's say 4 dx. You are correct. It has to be a 1/4, doesn't it? So if I think about integrating e to the u, I'd have 1/4 integral e to the u. So it integrates to itself. E's are nice, aren't they? They are themselves. So it's going to be an e to the 4x, and then I have to adjust because it's more than just an 1x, it's 4x, so it's a 1/4 e to the 4x. So let's go into the pattern. I'd rather be down here. U times v, multiply across. That's going to give me a 1/4 x squared e to the 4x. Take away the integral of, come across the other diagonal. I'm going to write it. It's a 2 times a 1/4 integral e, I should have a dx there, x e to the 4x dx. Ew. 1/4 x squared e to the 4x minus 2 integral x e to the 4x. This one, not so easy. I wish that we didn't have that there. Then I could integrate it really nicely. But it is there. So guess what? We go into another pattern of integration by parts. All right, so we get to do it again. Oh, it makes us happy. Okay, so set up a new U. This is going to be my U. This is going to be my dV. U equals x, then du equals dx. dv equals e to the 4x. And the integral of that is a 1/4 e to the 4x, because we had done it earlier, right? So I'm going to repeat in blue the previous stuff we knew. And now, coming in pink, we have a new u times v minus the integral of v du. U times v, 1/4 x e to the 4x minus the integral, come across the diagonal, and I'm multiplying 1/4 e to the 4x dx. Oh, yay, because I can actually integrate that. Do not let yourself get tripped up with the algebra part of this. 1/4 x squared e to the 4x. Distribute through, correct? And it's a -2 distributing, so I get a negative 1/2 x e to the 4x. Negative times negative makes positive 1/2. Now I've got to integrate e to the 4x, which is a 1/4 e to the 4x plus c. So here's this integral right there. One last cleanup sweep, and we are done. This one required 2 integrations by parts. They can take more than that. So, yay for us. Why do I have, am I off? Because I have a different answer on my sheet. Did I get off somewhere, you guys? I have 1/8 in the middle, trying to see where I might have messed up. That 2. Oh my gosh. No, that's fine. 2 times 1/4. Oh, dang, right here. You guys probably saw this the whole time. That was a 1/2. 2 times 1/4 is 1/2. Okay, I got to clean up my work and then distribute it through. There's a 1/8. Distribute it through again. And we are at 1/8 again. And then 1/8 times 1/4 is a 1/32, and I also need to replace that. Oh, I'm glad I checked the answer. Oh, that was crazy. I blew that. Sorry about that, guys. Hopefully you can follow that little mistake I had, where I took 1/2 times 1/4, or 2 times 1/4, and got a 2 out of that. Alrighty. Repeated integration by parts. All right, there it is. Sometimes these end up being circular. So I'm going to make this kind of my last one, and then I think we'll finish the rest of it tomorrow, because this gets kind of long. All right, let's let u equal e to the x, or should we? Lie 8 would say trig before exponential. In this case, it doesn't really matter. But you know what? You guys would probably do it the other way, so I'll do it the other way. Cosine x, trig before exponential, and then dv is going to be e to the x. du equals negative sine x dx with respect to x, and then the integral is just nice e to the x. This would have been a dx there. So this is my u, and these two parts became my dv. Set it up. U times v, e to the x cosine x, minus the integral, come across the diagonal. We get minus minus changes to plus, e to the x sine x dx. Ew. Okay, that's almost similar to what we had in the start. Another integration by parts. Another integration by parts. So if I set my u to be the trig function, you must stick with that same pattern. So du equals cosine x. Continue to choose trig function for u. Okay, that's important. dv will become the sine of the e to the x dx. That integral's easy, it's e to the x. All right, so e to the x cosine x plus, here's my integration by parts, u times v, e to the x sine x minus the integral of the other diagonal, e to the x cosine x dx. So this is our u times v minus the integral of v du. Another integration by parts. And you're like, oh my gosh, this never ends. You would be correct in that. What I want you to do, it does end, but it's kind of interesting how this ends. E to the x cosine x dx, our original problem, is equal to e to the x cosine x plus e to the x sine x minus the integral of e to the x cosine x dx. Wait a minute. We've already done. We have a match here, do we not? Okay, so algebra kicks in. Use some algebra. We're going to do an equation solve. Add like terms. Add a like term to each side of our equation. And now we get two integrals of e to the x cosine x dx. It's like we're making this stuff up, isn't it? E to the x cosine x plus e to the x sine x. We're so close. We better get a plus c in here, huh? Now, I don't want to know the answer to two integrals. I just want to know the answer to one integral. So we will, there's an equal sign here, multiply both sides by 1/2. And final answer, e to the x cosine x dx equals 1/2 e to the x cosine x plus 1/2 e to the x sine x. Half a c is still a c, so we just got a new c. There's our answer. I think of these as being circular style because they do wrap around. And they're very easy to predict. E to the x has a derivative that never ever ends. Cosine x has a derivative that never ever ends. They both integrate super easily. They're easy to spot these circular styles. All right, 23 minutes. That is plenty for the day. We will continue with this tomorrow. You can start, though, let's skip that. There is a worksheet, and it is not my math lab. This one. This is in your packet. So go ahead and work on these. You'll probably be able to do quite a few of them. The one thing that we haven't done is the tabular style. So I will show you that tomorrow. Good day.